In this last section, we are going to look at what we call solids of revolution. So, what a solid of revolution essentially is that we are going to take a two-dimensional region, usually bounded by two curves or something like that, and we're going to rotate it about an axis. So, we're going to take that entire two-dimensional shape and spin it around this axis, which would then create a three-dimensional solid. So the question is, what can we find for the volume of that figure? Now, this is probably the most visual spatial thing that we do all year, which is why for some people this ends up being the biggest challenge. But let's kind of focus in this first video on just getting an understanding of what we are doing. So here is a rectangle, a very simple region, okay? If I want to rotate this about the x-axis, that means I'm going to keep this bottom connected to the x-axis, and I'm going to take this rectangle and rotate it towards myself. So imagine it falling forwards out of the screen and turning around that x-axis. So I'm going to do this first coming straight at you. So here's what will happen. We can see it kind of falling forwards and going all the way around. And if you can kind of imagine what sort of a three-dimensional shape this is making, let's look at it from a different perspective. You can see here that we're getting like a cylinder, a pretty flat, almost like a disc. Okay, so let's put this back and watch this from the side now. This thing is kind of weird. So if I rotate now, you can see where this is happening. And we want to consider this all filled in, like this is a three-dimensional solid that we're looking at here. So that's a pretty simple one, but we're going to look at lots that have all kinds of other shapes. So here's another region that we have. Okay, so we have some sort of curve right here. Maybe it's a cube root. I don't really know, some sort of polynomial. And it looks like its lower boundary is the x-axis. So once again, if we're going to rotate this about the x-axis, we're going to keep the bottom connected to the x-axis, and everything else we're going to spin around, creating this solid figure. So let's turn this a little bit so we can get some better perspective here. So when we rotate, maybe you can kind of imagine what this is going to look like. It makes this sort of funnel shape. Now, a cylinder, we have a volume formula for a cylinder, but this funnel shape, we definitely don't have a volume formula that would find the volume of this three-dimensional figure. And so that is where the calculus comes in. Now, let's look at just this region. Okay. When we looked at just the definite integral for finding the area under that curve, we looked at Riemann sums, which uses rectangles, okay? So we divided this region into a bunch of little tiny rectangles like that. Oops, too far, too far. We don't want to do that just yet. Just a couple rectangles. Let's see. There we go. All right, well, you can see what we're doing here. So all of those little tiny rectangles, we saw again in this first one that when you rotate a rectangle like that, you get a cylinder, or what we would call a disc when it's flat and skinny like that. So here, the idea is going to be the same. We're going to start by looking at all of these little tiny rectangles, and we're going to rotate each of those rectangles around the figure, so we're getting all of these individual discs. And that is what we're going to add up. Now, here's just the discs. Looks like that, okay? Now, if my discs are very wide, you can see it gets less and less accurate compared to that shape, which is why we want our discs to be very, very flat. Again, it's that idea of slices of bread. And like we talked about last week when we looked at different shaped cross sections, we want the width of those discs to approach 0. So essentially, we're just adding a bunch of 0 width discs. So just a bunch of circles over this interval from A to B, and that is how we are going to find our volume, okay? Now, the last one that I want to show you is both of the examples that we looked at first revolved around the x-axis axis, but they do not have to. You can rotate around any line, horizontal or vertical. We'll look at some vertical examples here a little bit later on. But in this case, I want to revolve this region around the line y equals 1, which is going to be the horizontal line right here. So we're going to keep the base of this solid around the line y equals 1. I'm going to add the discs in here again. Well, let's look at just the shape first. And when we rotate, you see we get kind of this egg-shaped solid. Let's look at that from the side here. So when we rotate, we're getting this figure, kind of like a football. And then we would do the exact same thing. We would break this up into discs, and we would use that to help us find our volume. So keep these visuals in mind as you start working through your notes, because this is what you have to imagine is happening whenever you look at these, because you're typically only going to be given this initial two-dimensional figure. And from there, we're going to be able to extrapolate what the volume is going to be. So to kind of sum this up, in a solid of revolution, each cross-sectional slice of the solid is going to be a circle, okay? So using thinner and thinner slices, like we've talked about, we want this delta x to approach 0, then we can use the definite integral to find the volume. So we've talked about this idea before of a representative rectangle. That's going to be really important because these are the rectangles that we're going to revolve to find the disk, okay, that we are going to use. And so it makes sense that what we are going to use is called the disk method. And so the disk method for finding volume looks like this. Because the volume formula for a cylinder, if we go back up to the top here, the volume of a disk or a cylinder is going to be the area of the circle times the width of the disk. If you remember from geometry, the volume of a cylinder is pi r squared, that's the area of the circle, times the height. Well, these cylinders are all on their side, so that's why we're saying width. And so the volume formula is going to be pi times the radius squared times the width, where r is the radius of the disk. Now, if we look at this diagram, the radius of the disk is going to be the height of your representative rectangle, okay? And so that is where these formulas come from. If we are using a horizontal axis of revolution, the disk method, the height of our rectangle is going to be the radius, which is typically going to be where your function goes. And that is what's going to go inside here. The pi from pi r squared h, or times the width, is just a constant, so we can pull it out to the front. You're going to integrate from a to b. And then we want the radius squared, and then times the width, which is your dx. Dx, that's your delta x right here. That is the width. So this is pi times the radius squared times the width. And we're doing that all over that interval from A to B. Now, it does not change at all if we go to a vertical axis of revolution. It is just going to be dy instead of dx. And just like with the slices, this last little note is really important. The representative rectangle is always perpendicular to the axis of revolution. So if you are revolving about a horizontal line, that means your rectangles are perpendicular to a horizontal line, so you're going to go dx. If you are revolving around a vertical line, then you have to do your integral dy because your rectangles are going to be perpendicular to a vertical line here. So that's going to help us set up our pictures. Okay, so that's sort of a visual overview of what we're going to be doing. And in the next video, we'll start looking at some examples of setting up these integrals.